Okay, let's get started here. I think we are hoping that we'll post the first assignment probably either today or early tomorrow. And it's going to pretty much follow what I'm going to cover this week and possibly early part of next week. And so we are going to begin with some sort of transaction data. Okay. And once we have the transaction data, we are going to try to aggregate this data in terms of some sort of small discrete time units so that you can use traditional time series methods on the discrete time series data. Okay? So there is no reason why we should go from this kind of data which is supposed to be based on point processes to discrete time series. But point process data tends to be very noisy. Okay, it's very difficult to see the signal in that noise. So once you go to the discrete time series, a few concepts come very easy. So that's one of the reasons we want to do that. Okay, so once you go to the discrete time series, I think there are few concepts that I would like you to know. The first one is, I think if you look at for any stochastic process, there is a mean function, there is a variance function. You can have functions of higher order too, but in finance, I think the focus has been on mostly the average and the variance. And the autocovariance plays an important role because autocovariance tells you the dependence of successive time observations. So you can use that information to predict into the future. So that's where I think the autocovariance come into play. Again, like covariance, as you know, in the regression context, covariance is a linear measure. So if the covariance is 0, doesn't mean that there is no correlation, just means that there is no linear correlation. There could be other correlations. Okay, so I'll try to bring some nonlinear time series ideas later into the course. First, I think to start with, we'll go with the linear time series course. Okay, linear time series ideas. So if you look at this autocorrelation function, all these things are defined in very general terms here. Since we have only one realization of time series, it's not possible to calculate these things. You really have to do something more generic than that. So this is what this probably is the most useful concept here. So time series yt is supposed to be weakly stationary if the average is a constant and the variance is supposed to be finite. And you can also see that gamma h is the covariance between two time points yt and yt minus h. It depends only on how far these time units are apart. It does not depend upon where they are in the time series. Okay, so that is the autocovariance. Autocorrelation is the autocorrelation function is just the ratio of the covariance divided by the variance. Okay, again I must tell you that this autocorrelation function, the way I have defined it, is valid only when you have autocovariance finite. So when the series is non-stationary, you will see that autocovariance increases as you go along, right? So it's not going to work out. Okay, why is this important in algorithmic trading? Stationarity is an important concept that we'll come back and reuse it. So the idea being is that the time series is supposed to move around certain average level. So if it deviates from that average, that means that you can make the trade so that it will come back to the average. So that's the idea behind it. Okay, so I'm going to ask you to think about couple of things here. Okay, and what are the properties of this autocorrelation function? Autocorrelation function, you'll see that all lags should be less than 1, and it's an even function, which means that whether you're relating t minus h to t or t to t plus h, it's all going to be the same because of the stationarity condition that I mentioned here. And you can also show that if you construct this correlation matrix out of it, it's going to be a positive definite matrix. Okay. So I'm going to take a simple example and show you how to check whether it is stationary or not. Okay, just to give you a practical idea here. Okay. Any question? Any question here? So I have this data. I think I posted on the coursework site. So this is the exchange rate data which I've been using before. Something is not right here. So I'm having difficulty with a program that kind of, whenever I store it as a comma separated file, it sort of goops up a lot of things. I don't know what to. So let me, I think I have another place where I can get this. I'm going to, okay. So let me copy and paste it in many tabs so that I can show you. Yesterday also it happened. Sorry, I'm having difficulty. I don't know why. It's not coming through. I'm sorry. I think it's just worked in my office. I just checked it before I came. Now it's not. It's not coming through. No. I'll show you a different example. I think it's a.
You can open it with Notepad.
With?
With Notepad.
With Notepad? No, I can open it. I'm trying to get this program Minitab so that I can show you some plots. That's not coming up here. Let me give another example. I think I have one other example so that you can see. Now that I have it here. This was going to save it for a later time, but let me show you that. Okay. So this is supposed to be a exchange rate data that I've used for weekly exchange rates. But I think the diagrams on here are the most important ones. Okay. So when I look at the exchange rates, this is actually in R. You can see that the first graph is supposed to be exchange rate over time. So when you look at this graph, is that stationary or non-stationary? How do you check for stationarity? Roughly the idea behind stationarity is that if you take this entire duration and split it into small groups, the average should be roughly the same, right? So when you look at this graph, you can see that it's coming down and going up, and at any given duration, given interval, you'll see the averages are not stable, right? They are changing. right? So if that is the case, we can clearly see that the process is non-stationary, okay? But if I look at the autocorrelation function, you can see autocorrelation function is given in the second graph there. The way I think R is set up, autocorrelation at 0 is always going to be 1 by definition, right? So you have to ignore the first column there. Look at rest of the bars that's given in the second diagram there. So what I'm talking about is this graph here, okay? So what kind of autocorrelation function do we get there? You can see autocorrelations are very close to 1. Can you see that? Okay. So the test we are going to use for checking whether it is stationary or non-stationary is to check if the autocorrelation is equal to 1. Okay. So that's one of the important difference between using in regression and time series. In time series you have this additional constraint that you need to worry about. Okay. So how do you make this process stationary? What is the way to make the process stationary? Use the first difference series, okay? Sometimes what happens when you use the first difference, you may wipe out a lot of information, okay? Be careful about it, okay? So the key tool that we are going to use here is this. We said P of t is, if you remember yesterday I defined this as log of P of t. So we are going to take the difference. So the difference by definition is nothing but the return on the series, okay? P of t minus P of t minus 1. Okay? So if you look at the second graph here, this is supposed to be the return series. Okay? So what is the autocorrelation function of the return series, which is given in the next diagram here, and you can see, is there any autocorrelation there? So you will see that usually there are two lines that are given. Those two lines are supposed to check whether at any level the autocorrelation is 0 or not. Okay. So those lines are drawn mainly based upon this simple rule they use. So that lines are nothing but plus or minus 2 over square root of t, where t is the total number of observations that you have. Okay. In some softwares you'll see it's very narrow in the beginning, it gets wider afterwards. Those intervals are valid only if you have small samples, and you can use them, but I think it doesn't make too much difference when you have large number of observations. Okay. So checking for stationarity is going to be checking whether the autocorrelation is equal to 1. Okay. So there is also some model based test people use in practice, which we'll cover little later. Okay. So when you look at this checking for non-stationarity, mainly I tend to use the plot. I also tend to use checking whether the autocorrelation is equal to 1. Okay. So there are few simple models that I want to introduce here. Okay. The reason I want to introduce them here is that you will see when we use high frequency data, you will see that there is some correlation, autocorrelation in the returns. Okay. And those autocorrelations come for various reasons. One of the reasons I mentioned was that because of market frictions, they come. They can also come because of the bid-ask bounds. Okay. And the various reasons, there's about at least 10 reasons that are attributed to that. Okay. How do you get that? Usually you can see that it comes mainly because of the moving average type of relationship. Okay. So if you look at this, you'll see the moving average is yt is supposed to be mu plus some sum of two random errors, epsilon t and epsilon t minus 1. Okay. And the key is that epsilon t is lagged one time to get to that model yt. So you can show that when you do this, covariance between yt and yt plus s is given by this quantity here. The key is this quantity here. You'll see that covariance is positive when S is equal to 1 and it is 0 if S greater than 1. So which means that the autocorrelation tends to last only for one period, afterwards it vanishes. Okay. So there are two types of models we are going to see. One is the autoregressive model, the other one is the moving average model. Okay. And I'll briefly give you how to distinguish between those two. But in real life, the data is never going to fall that cleanly, either one of them. It's going to be a mixture of the two. Okay. So just to give you why this moving average model is important in real life, I want to briefly mention that how this works. Okay. So let's assume that the true price is supposed to be given by this quantity here, and if the market is efficient, the true price is supposed to follow random walk model. So this is epsilon t. Okay. So the prices will change only if there is new information. So this epsilon t is supposed to be information. Okay. But you don't observe the true price. What you observe is what is exactly transacted. So the observed price is supposed to be true price plus some quantity ut. I'm going to call this ut as market friction. Friction in the market. Okay. So if you look at the difference series P of t minus P of t minus 1, you can see that this is given by Pt star plus ut minus Pt minus 1 star plus ut minus 1, and Pt and Pt minus t star from the first equation gives you epsilon t plus ut minus 1. So this is supposed to be the actual return that you observe, RT. So what is the covariance between RT and RT minus 1? If there is no market friction, you know that this quantity is going to vanish, right? RT is going to be completely random. And because of the market friction, you can see some of the last period information is carried over to this period. So because of that, you can see that covariance between RT and RT minus 1, RT and RT minus 1 is given as covariance between epsilon t plus ut minus 1. For RT minus 1, you can show this is epsilon t minus 1 plus ut minus 1 minus ut minus 2. So if you look at the covariance terms, you see that there is a common term between the two that introduces negative correlation in the data. So you can show that this is a negative covariance. Okay. So if you use the high frequency data, generally you should see there is a small negative autocorrelation, and that's mainly attributed to the market friction. Okay. So moving average models come very handy to test if the market is efficient or not, and the commonly observed phenomena is that they tend to be small negative autocorrelation. Okay. So we talked about this non-stationarity a little bit. Non-stationarity can come in many different ways. It can come in levels, it can also come in variance. Okay. What do we mean by non-constant variance? Again, the same idea that I mentioned before. If you take the entire duration of the data, put them in small intervals, compute the variance for each interval, you should see the variance is shifting. Okay. And so it also means that changes in autocorrelation structure. Okay. And so here is an example that I would like you to think about. So this is a model that I have yt is equal to yt minus 1 plus delta times plus delta plus epsilon t, and you can go through the calculations, but the main point of the that slide is the following. So let me write it in terms of the price. I think remember I mentioned we have the random walk model p of t minus 1 plus delta plus epsilon t. That's the model we have. Okay. So what kind of model is this? This is a random walk model with a drift. Can you see that? Delta. Okay. So essentially if you rewrite this, you will see you're looking for drift in the written, and you'll see that most of the algorithmic trading rules tend to look at short-term data to see if there is any drift in the data. Whenever there is a drift, positive drift would mean that there is a momentum, right? And negative drift would mean that you should be able to get in it. The contrarian strategy could be used here, okay? And you can show that even with the drift, you can see that it's going to be a non-stationary series. So the average yt is given by delta t. That means that the average increases at the rate of delta over time, and variance is given by t times sigma squared, and covariance term and correlation terms depend upon the ratio of s and t, how far you are away from that. Okay. So it's not independent of s and t. Okay. So that's one of the things that I want you to remember. Okay. So just to give you an idea here why variance is important. Variance is nothing but square of RT, and let me go back to this graph here, which we will revisit later. Okay. So this is the written data, RT data, and we saw that there is no autocorrelation in the written, and this is supposed to be RT square, okay, written square, which is supposed to measure volatility of the series, okay. But when I look at the autocorrelation of this RT squared, what kind of autocorrelation do I get? Or all of them within the 2 standard deviation bounds? You can see that there are some autocorrelations away from those lines. Can you see that? So that clearly indicates that although you cannot deduct any linear dependence in the written, you should be able to deduct some dependence on the variance, RT squared. Okay? So that is the focus of research for the last several years on the so-called arch and Garch models were developed using that concept. So there is some dependence on the variance. Okay? How do you use that information? It just tells you that if there is volatility in the time series or volatility in the price series, you will see that volatility can persist for a while. Okay, that's the main idea behind it. Okay, so let me go back here. So the previous slides I think mostly goes through population time series information. Here I think we have sample data, how do you estimate them and so on. Okay, the main point of this is that if you have a time series and if you want to estimate the average, you can see that the variance of the average actually depends upon not just the variance, it also depends upon the autocorrelations too. Okay, and this is some sort of small sample result for variance of the first order autocovariance term. Okay, so again, estimation of the average and all these things are suspect if you have a non-stationary process, because the average is not, doesn't exist. Okay. Okay. So I want to briefly comment on what kind of models are used. So far what we have seen is mostly computing some sort of descriptive measures like average, correlation, covariance and so on. Okay. So there are 2 types of models we are going to see, and without getting too much into the details, I want to motivate why, when and how you use them. Okay. The first is the AR model. Okay. Just to illustrate this, I'm going to take an AR1 model, autoregressive model of order 1. Okay. So this model, you could write it as yt is equal to some constant term. For the time being, I'll ignore that, put it as yt minus 1 plus epsilon t. So this is the AR1 model. AR1 model. Okay. This is like a regression model, right? Yt and xt, except that when it comes to time series, in order to make the stationarity hold, you need to make some assumptions on the coefficients. So what is the assumption on this pi coefficient? This is almost like a constrained regression in a way. The constraint is going to be on this coefficient. What is the constraint? It's non-zero, then otherwise there is no model. But is there one other constraint? What is that? This coefficient should be always less than or equal to 1. Should be less than 1 for strict non-stationarity. Okay. Be less than 1. So if it is equal to 1, that's what we are talking about, unit root non-stationarity condition. Okay. So what is the property of this? I think you can show that if you look at the autocovariance between t and t minus h, so let me write a correlation between yt and yt minus h, which is given as rho of h. You can show that this is supposed to be pi to the power h. Okay. Okay. So if pi is close to 1, you can see that pi to the power h is not going to die very soon. Okay, that's the reason why we saw that graph we saw, remember, for the first series. Okay. So this is supposed to be pi to the power h. Okay. So autocorrelation function, from the pattern of the autocorrelation function, you should be able to guess what could be the value of pi. Okay. And the other model that you should know here is the moving average model. Okay. What exactly is the moving average model is that yt is equal to epsilon t minus theta times epsilon t minus 1. So that is a moving average model. And you can show that covariance between yt and yt minus 1 is going to be covariance between epsilon t minus theta times epsilon t minus 1, and then this is t minus 1 minus theta times epsilon t minus 2. And because of the common terms between the two, you can show that this covariance is given by minus theta times covariance between t minus 1 and t minus 1. So let's assume that that's given by sigma square. Okay. But the key is the next term here. What is the covariance between yt and yt minus 2? What is the covariance? Is there any common terms between t and t minus 2, yt and yt minus 2? If you look at yt, you see that this is a quantity. Yt minus 2 is going to start with epsilon t minus 2 minus epsilon t minus 3. You can show that this covariance is 0. Okay. So for the moving average process of order 1, you should see the first order correlation should be, non-zero. Rest of them should be 0. Okay. So one way to identify moving average process is to use the autocorrelation function. Based on that pattern, you can decide what is the order of the autocorrelation function. Okay. In fact, you can show that if you have moving average process of order 2, So if you have moving average process of order 2, which is given as yt is equal to epsilon t, t minus 1, theta to epsilon t minus 2, you should show that covariance between t and t minus 3 onwards would be 0. Yt and yt minus h should be 0 for all h greater than or equal to 3. Okay. So quickly to identify whether you have a moving average process, you can use the autocorrelation function to decide how many lags you want to include. Okay. So how do you distinguish between pure autoregressive model and pure moving average model? What quantity would you use for identifying that autoregressive model? Anyone?
The autocorrelation function S.
But autocorrelation function, as I said before, I think if depending upon the value of pi, it may never die down. If pi is 0, it will die down quickly, right? But there's one other tool you can use in order to identify the autoregressive process. Okay, so let me briefly write what I mean by that. Suppose the true model is, this is the true model. Yt is pi 1, yt minus 1 plus epsilon t. But you force a model on the data, say fitted model. Fitted model is yt is equal to pi 1, yt minus 1, pi 2, yt minus 2 plus some t star. Okay. If that is the case, what kind of number you should see for pi 2? This is a true model, right? And you're forcing this model here. What kind of number you should see for pi 2? Should be 0, right? Okay. And if you can fit this model and decide how many lags you want to include, right? You can fit a AR5, 6, whatever number you want to fit, and check how many of the coefficients are 0, drop them out and refit the model. Okay, that's one way to do it. Okay, but I think some of these calculations are already done for you, so they use what we call as a partial autocorrelation function to identify autoregressive lags. Okay. What is partial autocorrelation function? It's nothing but looking at the correlation between t and t minus 2 after you account for the information coming from t minus 1. Okay. So essentially regress yt on yt minus 1, compute the residuals, regress yt minus 2 on yt minus 1, compute the residuals, see if there is any correlation between the two residuals. Okay. So all these calculations are sort of automated. You don't have to fit sequentially and then decide how many lags you want to include. Some of these things are already done for you, so you can go back and look at the partial autocorrelation function. Based on that, you can decide how many lags you want to include. Okay. Having said all this, I think for financial data, you will see that generally it tends to be non-stationary, and one level of differencing will wipe out all the information there. It's all going to be stationary. But at the high frequency level, I think there is some hope that you can model, using moving average process. And the other hope we have is that you can look at the variances. Variances have some structure to it. Okay. So some of these things are, a little bit, you don't need this many tools to look at financial data because they tend to be a little bit more simplistic than what these models would suggest. Okay. Any question? Any question? Okay. Leo, you want to take over?
Sure.
Okay. So I think Leo is going to demonstrate how R works, and then if you have any questions, you can talk to him. You want to use?
Yeah. Hopefully I can,
Why don't you use yours?
yeah, that's fine. I can use mine. Just hopefully I can plug it in. Should,
You're supposed to use this one.
Okay. Sounds good. Hi guys, I'm Leo. Plug this in real quick. I'm sorry, I'm supposed to use this one? Okay. All right, so as Professor Velu mentioned, we're going to be using R for the majority of our assignments in this class. You can definitely feel free to use other software if you're more familiar with it, but I think it'll take you considerably less time if you use R. Right, so it's going to be a combination of both slides, and I'm going to show you some stuff in the actual software. Right. So first of all, like, why do you use R in the first place? It's a free software environment for statistical computing and graphics. The main reason people use R is because there's a ton of libraries you can download for it. And just for this class, we're going to use libraries to both read, clean, and interpret high-frequency trade and quote data, run various autoregressive models, run multivariate regressions, analyze correlations, plot and interpret results. You can definitely code all of this up in Java or Python or whatever, but if you wanted to do this all from scratch, have fun. With R, you can just get all of it for free, so you can start from a pretty good high ground. And the second part is if you want coding help, can help you much easier in R code than anything else. Cool. So definitely the beginning part. If raise your hand if you have downloaded R or used R before. Few people. Okay, so for those people, the beginning part of this might be kind of review, but eventually we'll actually get to how we can download high-frequency trade data and use a high-frequency package in R to clean it and process it. So that'll be the last part. Okay, so for those of you that don't have R, you can go to this site to grab the latest distribution. I think I should have, yep. If you go there, you come to this site, download the distribution that you want for your operating system, you're good to go. And so while it's not required, I highly recommend you guys get RStudio. So what RStudio is a wrapper, an editor that kind of like sits on top of R. And it is here at this site. All of the slides and the material will be posted on coursework, so you can go and take a look at it. And so let's see what RStudio looks like. Okay, so this is RStudio. If you've used R, this looks a tiny bit different. A couple more windows, but still the same idea. So R is meant to be a language with an interactive terminal, right? So there's my terminal. If I want, I can type whatever commands I want to, and it'll evaluate them in real time. But pretty quickly, if you want to write multiple commands, especially for the homework assignments, you don't want to type them all in the terminal. So R has these things called R scripts. And so this is an example of an R script, and we're just going to go through some of the programs one by one to tell you guys what all the different programs commands do. Okay. Right. So a little piece of advice when you write R scripts. So a script is just a collection of R commands that you can evaluate. Always useful at the top to write what the thing is, who you are, and what the thing does, because I can guarantee you if you want to reuse one of these scripts like a year later, if you don't write this, you'll have no idea what this does. And chances are you won't actually reuse it. So something like this, a little header is always helpful, just good general programming practice. Second thing, really important, is how to get help. You're probably going to get stuck at least a few times using R. And so R has a really nice functionality where you can type a question mark. Can you guys see this, or is the text too small?
Too small.
Too small, okay. Let's try. Be a little tricky to see a lot at once, but is that easier to see? Okay. R has really nice functionality where you type a question mark and then any command. And so, by the way, in RStudio, you don't always have to type any command in the console. If you click on whatever you have in your R script, and at least on a Mac, it's Command Enter. I think on a PC, it's Control Enter. It just runs the command in the terminal. And so what that gives you is when you type question mark in a command, you'll see help documentation, and hopefully I can, yeah, there we go. All right, and this is what our help documentation looks like for any command. Show you the name of the command, description of what it does, and this part is actually really useful. It tells you all the different variables or parameters a function can take. So if you're ever wondering what other things you could do with a mean function, well, you can do a trim mean, you can do something about removing missing data from whatever you're taking a mean of, and it tells you what all the arguments does, the value, and see also commands that are related to it. And so general rule of thumb, if you don't know what an R command does, look up the help file. That'll usually help you. Okay. Right. Of course, beyond that, Google is your friend, and generally answers that are posted on Stack Overflow, I don't know if you guys have seen that site before, but those tend to be pretty good. So, value those over other sites. Cool. All right. Again, commands to manipulate variables and do simple math, right? 1 + 1 give you 2. Well, of course, you may want to assign that to a variable. So if we take x equals 1 + 1, you'll see over on this right-hand side, there's actually a visual representation of the environment in R. So I see I've created a variable x with the value 2. If I want to reference it again, I get 2. A lot of the power of R is a computing language, so you're pretty quickly going to want to get to vectors. And so this is how you define a vector. And so we see it's 4 numbers, 1, 2, 3, 4, all stored in this vector. A lot of this stuff you're probably not going to need to interact with at a low level, but whatever commands you do run for your homework assignments will be built up of these things. Right, so if I want to look at one particular value of a vector, I use bracket notation. If I want to look at a series of values, but not all of them, and then if I want to replace a value in a vector, I do the same thing. And so now if I type a vector, I'll see 4 replaced with 99. Okay, so far so good? Cool. So this guy is a very useful command to remember in R. So I think str stands for structure. And so whenever you have an R object that you don't know what it is, you don't know what information it has, you can type in str and it'll tell you, hey, this thing's a number. It's an array of numbers, and these are the 4 numbers. We'll see a little bit later. Yeah, question?
So in R, they're all indexed from 1 instead of 0.
Yes. Right. So if you're used to different programming languages like JavaScript or something, usually arrays start at 0. Yeah, R starts at 1. I don't know. I think MATLAB does the same thing. I'm not sure. Right, so this gives you the structure of any R object. For vector, it's pretty simple. Later on, we'll see more complex structures. So one good thing to remember, math is by definition entry-wise, right? So if I write this command, every entry in the vector is divided by 100. If I type this command, it'll actually, what it will do is it will multiply the first value in the vector by 0, the second one by 1, the third one by 0, and the fourth one by 1. Right? So this isn't matrix multiplication, it's entry-wise multiplication. Good to remember. But you can also do matrix math. So what I did with this M1 guy is I created this is a matrix of all ones. And so if I wanted to take the inner product, it's a multiplication sign surrounded by percentages. And so what this will do is it'll take the inner product, right? So the left-hand rule multiplication, and this is a sign for the outer product. So 2 vectors will give me a 4x4 matrix. Okay. So far, so good. If you look up our code online, a lot of times you'll see these arrows as assignments instead of equal signs. For all intents and purposes, they mean the same exact thing. So don't even worry about it. For the most part, when you work with data, you'll be working with data frames. Data frame is kind of like a matrix with named columns. And so, for instance, if I wanted to, I could make the following data frame. And so it has 2 variables, age and height, and generally observations are in the rows of the data frame. So if I want, I can access individual variables with the $sign. So that gives me the ages. I can add variables. So if I wanted to add a third weight, I could do that. And so now when I look at my data frame, it has age, weight, and height. Right? And this is how I access multiple variables. Maybe I just want like the last 2 columns. Well, so the notation for accessing matrices is you put commas in between the different dimensions. The first dimension, this guy that I left blank, is rows. The second one is going to be columns. And so I want all the rows, comma, the columns that are named age and weight. And so here I use the vector notation to denote that I want both of those. Right, and so that gives me the age and weight. Okay.
Sorry, can you repeat again why there's nothing before the comma?
Yeah, so for instance, this data frame is 3 observations on 3 variables. So for instance, if I wanted just the first observation and the age and weight of that one, I would do the following. If I want all of them, I just leave that blank. Yeah. Right. And again, all the code will be posted on coursework, so you can take a look at it. If I don't want to worry about names, I can just do column numbers. So that gives me the same age and weight. Right. And so if I wanted to access multiple rows instead, I'll leave the columns blank, and that gives me the first and third observation. Okay. So the point is a lot of our functions are designed to work with data frames. And so this is fitting a simple linear regression of the age on the height using data equals dat, the thing that we defined. So again, if we wanted to, we could do $LM to see what variables this function takes in. It says LMs fitting linear models. And so it takes in, and again, later on you'll get more familiar with this, but it takes in a formula, which is the actual regression, and the data, which is what we defined, and a bunch of other things that we're not going to worry about. Okay. So what this command did is it fit a linear model of age on height, stuck it in this dat.linearFit variable. Right? So if we take a look at our environment up here, we'll actually see that it created a new object that is a list of 12. A lot of times, if you want a nice formatted summary of an internal R function, like a linear model or something, or another fit, you can do summary. And so what it'll give you is exactly what it said. It'll give you a summary of what happened. This shows you the residuals, the coefficients that it found, the standard error, right? Neither of these were significant because we just had 3 observations. The R squared value, the F statistic, right? P-value to tell you if the regression is significant. Normally, this will give you a lot more information than just writing out the object name again. Because for instance, if we just typed the name of the object, well, all it would give us is this, right? A lot less information. Okay. Again, going back to the structure, say I wanted to pull a certain piece of data out of this linear model fit. So if I type in structure, it gives me this kind of crazy looking thing, but the whole point is that when I typed in structure, it told me, well, this is a list of 12 objects. So what a list is it's a vector, but every entry in the vector doesn't have to have the same format. So I could have a list of 12 things. The first thing could be a matrix. The second thing could be a vector. The third thing could just be a number. The fourth thing could be a string. And so this linear fit gave me a list of 12 objects. And after the $sign is the name of each object. So I can get out the coefficients. I can get out the residuals. I can get out the effects. I can get out the fitted values, and so this will be really useful if you want to do something with it. So, if I wanted to look at the fitted values, all I would do is write dat.linearFit, $, fitted values. One nice thing about RStudio is it has tab completion, so I can just type fit and tab. It'll give me the rest of them. So this shows me a vector of the fitted values. If I wanted to, I could use it in another R function or plot it or whatever. Okay, so reading and writing data. How do I read data from my hard drive and write to it again? Useful command is getwd. It tells me the directory that R is currently looking at. Right, and so right now I'm in my TA stats242 directory. If I wanted to change it to a different directory, I write set working directory. And so right now in this directory, here I'll show you guys. Okay, this is just my console. And so in this stats242 directory, if I look at it, there's a rates.csv file, and I want to read that into R. Well, so the way that I do that is there's a read.csv command. Write in the name of the file, and I say I wanted to put it into this rates object within R. Okay, so now I have this rates guy. I guess you can click on it and actually see what it does. I didn't even know that. Right, and so you see you have 4 columns. First the date, the different exchange rates compared to rupees, and all the different observations. And we're not going to do anything with this, but say I changed a bunch of data and I wanted to save it for later. Well, instead I can use write.csv. And first I write the data table that I want to write. Say maybe I only want the first 3 columns and the file name. And so if I do that, well, I already had this from before, but if I didn't, it would come up again. A little bit of intro into R functions. So you're probably going to get to a point in your homework sets where you want to reuse a certain calculation a bunch of times. It's both ugly and inconvenient to write the same 5 lines of code over and over. So it's really useful to use a function. And so the way functions are defined in R is you first write the function name. My function is a function of, well, the arguments that I'm going to put in. And then what do I do with the arguments? So always useful to write a couple lines about what the function does, because again, you'll probably forget in a few days. And so what this function does is it multiplies the 2 arguments and returns the caller of the product and plus or minus 10. Right? So it checks, is the product greater than 10? The absolute value, if it is, then you just want to constrain it back to 10, return the answer. And so this is useful if you want to apply a function to every element of an array. So for instance, say I have this array shorthand notation for all the numbers between -10 and 10. And so say I wanted to apply my function to all of these values. Well, sapply is simple apply. It's a useful command, again, if you ever want to see what it does, question mark, sapply, right there. And what this does, what this command does, is it applies this function to all the numbers between -10 and 10 for the first argument, and the second argument I constrain to be 2. Right. So first you actually have to define the function. It's not enough to just write it in the script. I actually have to execute it. And so now, right, it's actually stored in my environment. And I applied it to my function, and so what do I see? I see what I did was I multiplied each of the numbers between -10 and 10 by 2, and if they're greater than 10 in absolute value, I constrained them back to 10. Okay. One of the reasons I'm telling you guys this is you should always try to use functions like apply or matrix math. If you end up writing a for loop that runs over like 1,000 plus indices, it's going to take forever. And it's just because that's the way R is built. And so a lot of times when you write a for loop, if it's taken a really, really long time, you can probably rewrite it as an apply function and it will be a lot shorter. It's something to think about. Basic plotting functionality. So the main values, so R has this plot function. The main arguments it takes is the x values and the y values. Right, so these are two exchange rates, and this function, what it'll do is it'll give me a scatter plot. Make this bigger, yeah. And so I just got a scatter plot of one of the exchange rates with the other one. A lot of other parameters that you can change. For instance, I could set the title of the plot if I wanted to. And again, question mark plot will tell me all the different things that I can change. Okay. The last part of like the intro R stuff, we're going to be using a certain number of libraries. Again, like these are things that other people have already written, so you don't have to rewrite code. First, you want to install the package. It's done with this command. And what will happen is you'll see a bunch of text in your console saying it's installing it. Hopefully there'll be a success at the end. If it's a failure, you've probably got a problem. But then you want to load the library. And it may give you some warning messages, but what we just did is we loaded the high frequency library into R. Okay. Any questions about the R intro stuff? Pretty good? Okay. And so that's quite a bit to remember, and especially if you're new to R, and even if you've been using R for a while, there's a lot more in-depth stuff that you can learn. So later on today, I'll upload a zip file that has a bunch of references. And so the three, I think, most important ones, there's going to be this data manipulation with R PDF. Important chapters. Chapter 2 is all about reading and writing data, so much more in depth than what I talked about. Chapter 4 is how to work with dates. R has a special implementation of how it works with dates and times. Chapters 8 and 9 is all about data aggregation and reshaping. It's a little bit more advanced stuff, but it's pretty powerful for taking one data set that has all of its entries in rows and changing it into columns and matching between different observations and cleaning up a data set to be in the way that you want it. A couple commands instead of half an hour of wrangling. Introduction to R, it's pretty low-level stuff. You probably won't need it, but chapters 10 and 12 talk about writing your own functions and how to plot things. Might be useful. This R command 2 PDF is a summary of useful R commands. I think I actually have it open here. Maybe I don't. Right. So if you ever want a really quick refresher on what basic R commands do, it lists them out by types of commands, so how to do indexing, how to do different math functions, plots, statistical tests. You can have this open, refer to it back and forth. Oops. Okay. And this last one is a reference card specifically for time series analysis. If you want to read through it at some point, different functions that you can use for time series analysis. And I believe it tells you, right, all of these functions are from these packages, so you probably want to download those packages first. Right, decompose the time series, run different tests, stochastic models, graphics, autocorrelation, partial autocorrelation functions. We talked about those. Cool. Okay. And so the last thing I want to talk about is we've also included a few example R scripts. The best way to learn is by doing or by going through something that someone else has done. And so maybe really quickly I'll run over the first two. Later on you can look at them yourselves to get information. The last one I'll take a little bit more time because you're going to be following a lot of these steps for your first homework assignment. Okay, so what does arsimu.r do? I don't know, have we gone through the trading example in class yet or not yet? Okay, so maybe next week? Okay, so sometime next week you guys are going to go through a trading exercise, so how to build a trading strategy off of autoregressive processes. This is all the code for that trading example, and so if you ever wanted to go more in depth into that example and see how it works, here's the code. Also useful to look at like how to write functions. These are a little bit more in-depth functions, and a little bit more in-depth plotting could also be useful. Okay, the second one is time series examples. It's just a bunch of code that do different things you can do for time series. First one is just how to use different methods for linear regression. So this fits a linear regression to some heart disease data, plots the residuals, looks at different plots of predictors and things like that, does some model selection. So if you wanted to use a statistical procedure to decide like how many variables to actually include in the model. Also talks a bit of time series analysis. There is a CSV file that I think is daily returns in volume for Apple shares over a certain period of time. I think actually, did I lose my console back here at the bottom of my page? Ah, there we go. Right, so again, if I wanted to read the CSV of Apple shares, probably I'm not in the right directory. Let's just put it in the right directory. Here it is. Right, so this CSV is for a certain date range. It looks like it's pretty recent. Yeah, it's up to yesterday or a couple days ago, and gives you the opening, high, low, and close prices for daily trades and the volume, adjusted close price for Apple stock. So different things we could do with it. We could look at the correlation, the autocorrelation, partial autocorrelation. There's this test. I believe it's to test for autocorrelation. Let's check real quick. I think we'll talk about the box test later on in the class, yeah. Okay. to test for independence of a time series. Fit autoregressive models, and then do things that are slightly more sophisticated, like these ARIMA models that we'll talk about, GARCH models, etc. Right? So if you want a quick reference sheet for different things that time series functions that you can run and how they work in actual data, use this guy. Okay, and so the last one, the one that I want to go over a little bit more in depth, is how to actually get and load high-frequency data into R. And so high-frequency data is generally trade and quote data that's up to second increments or less. And we are going to get high-frequency data from this WRDS database. Talk about that one in a second. And so what high frequency is, it's a really nice package to analyze this data because, as you can imagine, it's a ton of it. And so getting it all into the proper format and cleaning it can be kind of hard. And so we're going to give one example. We're going to download trade data for Southwest Airlines, and Alaska Airlines between two dates, August 1st and September 1st of 2013. Then we're going to use the high-frequency library to parse the data and then plot the number of trades as well as the returns over this date range. Okay, so there are three required libraries. This high-frequency thing, time, date, TTR, you probably want to download them at some point. And so the first thing we have to do is actually download the data from the database. You don't do that through R, but here are the steps to do so. First, you go to the right location of databases in, this is a Stanford GSB site. Right, so Stanford Business, databases that start with W, go down here, you see WRDS. Now this part's kind of weird, but if you click on the documentation, it actually takes you to the database instead of the documentation. Don't ask me why. But probably it'll ask you for your login and password. Let's go ahead and do that. They're all stars, so you can't see my password, hopefully. Good. Okay, and so after you do that, you'll see this page. Probably the first time you go to it, or if you've cleaned your browser cache recently, it'll ask you for your email address. So just put in whatever email address you have. Email account at your subscribing institution. So it may need to be a stanford.edu address. If your email address doesn't work, feel free to put in mine. I'm sure it'll do the same thing. Then after you click on sign in, it'll take you to this page. And the only data set that we want here is TAQ, TAC data, I believe. Right. So this is New York Stock Exchange trade and quote data. And we are going to look at, is this right? Yeah, consolidated trades, thank you. Okay. And so again, all the instructions are right here. And so from here, I have a visual query editor where I can write my query for like what data that I want. And so in this case, I believe we wanted August 1st to September 1st of 2013. So go from August to September, not doing any filtering by time range. So, and then if I want specific companies, I go to code lookup. Usually if I type in the name of the company, I'll find the, oh, that's interesting. Oh, now it worked. Okay, usually if I type in the name of the company, like Southwest, we'll see a bunch of tickers that contain the name Southwest. This one's the one that we wanted. I want the ticker symbol, add code to the list. Okay, added one, say I also want Alaska Airlines, type in Alaska. Right, now I added both of them. I think you have to, if you want multiple companies, you have to do all this at once first, and then add all the codes to the query. I think the other way deletes your previous queries, it overwrites them. Okay, so I wrote this. Next step is which variables do I want to take? Just go ahead and click check all of them. You're not going to need all of them, but for some of the scripts later, I think it's useful to have all of them just so that the data is in the same format. And then finally, we want a CSV file. And click Submit Query. So it'll take a sec to process, create the output page. And what it should have done, it looks like it didn't, but what it should have done is given you a page that looks like this, that tells you the summary of your data request. After a while, it'll say your output is complete, and it'll give you this crazy looking CSV file that I believe is just some kind of hash, and this contains all the data that you wanted. All right, so you download it, you unzip it, and then you load it into R. So assume that we've downloaded and unzipped it. Now let's look at reading in this data with the high frequency package. Again, set the right working directory, reading the CSV file. You see how long this one took to load. This is only for 1 month on 2 companies. I think for your homework set, you'll have 3 months on like 4 companies, so it will take a while to load into R. But one of the issues is this CSV file isn't even in the format that high frequency wants it. So there's a little function here that I wrote that puts it in the format that high frequency wants it. And so all you need to do is go ahead and load this function into your environment. And then the way you run it is you type in the function, you type in the name of the object after you read it in, and the output location. So I want to throw it into this WRDS example place. I do this. Takes a second to run. So now if I look in my data folder, it's our WRDS. Right, it's now going to have 2 CSV files that has the trade data for each of the companies separately. That's how high frequency wants the data. Okay. Now, to actually use the high frequency package, you need to ingest it and output it in these extensible time series files. The way you do that is you write in your to and from dates in this format, the source file of the data, the destination file of the data, and then run this crazy looking command on each ticker at a time, right? This is actually 2 commands. And so what this is going to do after it runs is it takes that big CSV file and it actually parses the data into individual, I believe, days of files. Yeah. And so it makes a bunch of folders. Each folder corresponds to 1 day. And within that, you get these R data files, which houses the trade data for each of the tickers. And so this structure is what you're going to use to do inference on. Okay. As if that wasn't enough, to actually use the data, you have to load it back into R. So this is the load functions. And so within these 2 objects, I'm going to load all the data back in. All right, so how do we actually do something with it now that we have it all loaded in? Again, if I wanted to, I could look at the structure. And the structure is this XTS object, extensible time series. And if I wanted to look at something like the column names, I see that the data I have are the symbol, the exchange, the price, the size, the condition, CORR correction maybe, and this G127 thing. And I have that information for every single high frequency trade that's done. Right, and so actually this probably says in the structure. Right. right, and so there are over 400,000 rows in this XTS object. It's probably more than you want to deal with. Generally, when you look at high-frequency data, you aggregate it into certain time intervals. And so what this aggregate TS function does is it aggregates on a certain time interval. Right? In this case, we're aggregating the prices for the XTS data. Now, to get the number of trades, I take my function to be equal length, right? So it looks at every k equals 5, meaning 5-minute interval, and it looks at the number of prices in there, which is the number of trades. So if I do that in this object, I'll get the number of trades. One thing you may want to do is right now, it sets all the between trading day values. So there's a lot of values when trades aren't happening to not available, to missing data. You might just want to remove those whatsoever. This removes those values. And then if I type plot, what I'll get is, ta-da, a plot of the number of trades across the past month for Alaska Airlines. Okay. When does this class, how much time is there left in the class? 10:45. Okay. Well, it's easy to do the same thing with returns data, and the rest of this R script tells you how to do the same thing with returns data. It's very similar, but at least now you know how to get started. Cool. Again, I'm going to post this all in coursework.
Thank you. Thanks.